Thank you very much. So good morning, everybody. It's a pleasure. Can you hear me?
Yeah.
Thank you. So it's a pleasure to be here, and thank you to the organizers. It's always nice to be back in Cambridge. And today I'm going to talk from a kind of like a biology and statistical point of view towards a technique that is not new, which is model averaging, but how we can apply it for phylogenetics. So basically, let's see this here. So it takes a little bit. Sorry. This is going to be more or less the structure of my talk. So first, I'm going to make like a basic introduction because I assume that some of you maybe are not familiar with some of the concepts that we already been looking at this week. Then I'm going to get into model averaging. I'm going to talk about some software implementation. So I also think that developing software so users can actually use the methods is also quite important. And finally, so I'll make some caveats and thoughts and lucubrations about issues around model selection in phylogenetics. Well, this is not one. So models, basically, we can look at them as, obviously they are abstractions, right? Because the truth is unknown. The real process of molecular evolution is unknown, right? It's unreachable, so we just can approximate. But models, hopefully, they are useful to capture some essential features in the data. I'm going to talk today. That's not easy. About DNA models of evolution, basically, well, I'm going to consider models that worry about whether do we have equal or unequal base frequencies, whether do we have a proportion of sites that are invariable, right? Whether within the category of sites that are variable, there are sites that are faster, that evolve faster than others, and usually we use like a discrete gamma to approximate that with normally 4 categories. We can use more, obviously. And then, well, the pattern, right, of substitutions, whether changing from A to G is more common than to C to G, this and that, and the frequency is what gives names to the models, Jukes and Cantor, HKY, Feldstein 81, and so on. And most of you are familiar, right? So the most complex model I'm going to talk about is going to be GTR plus I plus gamma, and the simplest one is going to be Jukes and Cantor, right? Within those, there are 203 actually patterns of substitutions and base frequency, and we can get like, if I'm right, 812 combinations of all these parameters finally. So normally we don't explore all of these, right? So we explore a subset of these models. So why do we care about models? Because indeed models are important when we want to analyze real data. So obviously, depending on the model that we are using, we are going to get different estimates of different parameters. If a parameter is not in our model, we cannot estimate it, of course, right? So that's going to be important to describe the data. Distance calculations, right? The process of substitution is something that we cannot see, right? So there are hidden changes and so on, and well, use the models actually to correct for those unseen changes. So depending on the model, we may get with different estimations. Also, divergence times, right? So molecular clocks and so on. Hypothesis testing, right? We're going to do monophily tests, topological tests, tests of the molecular clock. They all depend on the models, right? Some depend a lot, and some they don't depend much, right? But maybe what is most important to us is whether models matter to the inference of topology branch lengths. And despite that there has been a lot of work on this, I don't think that we have a clear sense of whether models or how much they matter. Well, even better, I think that for me the most important question would be when they matter, right? Whether we could identify when we need to worry about the models and when we don't need to, right? In many cases, they don't. For maximum likelihood estimation, it's quite robust to model misspecification, right? But that's not always true, right? Depends on the topology of the true tree and so on. And also for computation of support, right? Rather, either bootstrap values or in Bayesian settings, posterior probabilities are depending on the model. So basically, everything we do in molecular phylogenetics, unless we are just using parsimony, probably, so depends on the models. And models, there are a bunch of papers showing that, they are important to consider. Right, so a little example that I'm sure you're familiar with this is like, well, we have models, right? But how many parameters do we need to include in our model to represent, right, or to capture the most important features in the data? Well, so a similar question would be, like was proposed 20 years ago, or maybe, or more, no? I don't know. It's like, how many points do we need to write an elephant? Obviously, that will depend on whether you ask a little kid or an adult, but I'm not sure if we can agree that probably this is not a good representation of an elephant, right? Just with 5 points, like using some polynomial or something. With 10 points, we start to make something that probably doesn't look like an elephant, but with 20, well, that might be some kind of, right, animal similar to an elephant. 30 points pretty good, and 36, we get with this Fourier transformation like a pretty good representation, right? So 36 would be like a nice number of points, enough to recover an elephant, although this could be cool, right? So, well, should we always add points to get a better representations of things? Should we always add parameters? So that's the main question that model selection tries to answer, whether, right, we need to add many or more parameters. So the key idea is that we need to add as many parameters as we need, right? Why? This is because, well, we have a few parameters, right? So we are going to have, well, quite a bit of bias, but the variance is going to be, the bias is going to be high, but the variance is going to be reduced, right, in our estimates. We are just estimating a few parameters, so, well, they are not centered around the true value, but, right, the error is low. But as we add more parameters, we are still working with the same amount of data, so there is a price to pay for that. So we are going to be able of taking into account more little features of that noise that is in the data, so we're going to get a better explanation of the data, so the bias gets reduced. But as I said, the data is still, we still have the same data, and we have more parameters. So the price to pay for that is that there is more error in each estimate, right? So what is the ideal point? Doesn't have to be necessarily this, right? That is not, doesn't have to be where this point crosses. So it's in some place here, we need to decide what is the number of parameters. And we use the parsimony principle, right, which is we want to keep things as simple as possible, right? That makes always or almost often makes sense. So I'm going to talk about there are more, 4 strategies to, from a statistical point of view, right, select what is the best model for us, right? So one of the first one that was proposed by Jack Sullivan and other people, and Hulsenbeck was using likelihood ratio test, right, in a sequential and in this case in a hierarchical fashion. Later, well, some people started to, Hasegawa and people from Japan basically started, right, in the 80s to start AIC, right, which is well-known also criteria. There is like a method that penalizes with the estimates of branch lengths that takes into account like performance, phylogenetic performance, by Jack Sullivan again. And then there is Bayesian model selection with BIC, Bayes factors, or posterior probabilities. Well, the basic quantity or the basic measure that we take to measure like fit, right? That's the idea of, well, the idea of fit is that elephant looking like an elephant or not, right? So that's in our mind. But here we try to measure that in an objective way. So we use like a likelihood function that normally, if we are worried about one of the parameters, right, we just worry about the models. These are nuisance parameters, and to get rid of them, either we maximize, we use the maximal likelihood estimates, or either we integrate. So this is a model likelihood in Bayesian settings. We integrate over all possible values of other parameters that are not interesting to us. And this, right, for the maximal likelihood kind of settings. Well, these are the hierarchical likelihood ratio tests. Right, you know that likelihood ratio test is, well, twice the difference between the complex and the simplest model, with degrees of freedom equal to the difference in the number of free parameters between those models. The thing is that, well, we could build a series of tests, right? So we're going to work like pairwise, right, comparing 2 models, and then making an answer whether we accept or reject one model and move, whether we accept. Right? We fail to reject actually Jukes and Cantor, so we move here. We make another question, which making questions here is adding parameters, right? And well, in this case, in this particular case, in red, this could be like maybe a possible path of decisions that, well, among all these models, the path, this concrete path with this concrete order of hypotheses, we will select HKY plus gamma as the most likely model. So this has been the strategy, the most used strategy, probably, the most popular strategy in phylogenetics for many years, right? But there are problems to it, right? And I reviewed those in 94 in a SysBio paper. Well, actually, I wrote a very simple tool that is not sophisticated at all, which is model test that calculates this, and probably that encouraged people to use likelihood ratio tests. But after a while, well, I started to add models or to this program, things like that, and I realized that, you know, that was using likelihood ratio tests maybe was not a good idea. So basically, there are problems like this, right? Like lack of global optima. I'll go into some of these. Like, well, obviously we depend on the significance level. We have a likelihood ratio test. We accept or reject a hypothesis depending on whether it's below some threshold, right? So there are going to be probability problems. That probabilities are not always well estimated. That depends on that hierarchy, whether we add or remove parameters, whether we start in the simple model or we start in the complex model and we remove parameters. That's similar to regression when we try to fit a model in linear regression. So the same idea. And, well, it's possible, but if the models are non-nested, that means that nested models means that one model is a special case of the other, that putting some restrictions in one model, in the values that some parameter can take, we can get the other model, right? If they are non-nested, it's kind of complicated to get those probabilities. I mean, we can do through Monte Carlo, it's like a parametric bootstrap, but that takes time and, well, it's complicated, right? So some of the problems, like very quickly, is like, well, sometimes there are no optimal solutions, really. We can have this situation, the arrow, like indicates which model wins in our likelihood ratio tests, right? So we can have this situation when normally we just would make these comparisons and we'll never care about this one, right? But if we do it, sometimes we can have this kind of situation. That's with real data, that happens. When there is no optimal model, right? Everybody's rejected against the other with some threshold, right? Then there is the question of the significance level. So we have the same data, right? This is the starting model. So using this threshold, we're going to reject this and reject this. So we move towards GTR. That's fine. But if the threshold is, we reduce the threshold, right? Maybe because we do a one-for-any correction because we are making multiple tests. Well, we wouldn't reject this test, right? So that's the difference here. That depends on the threshold. And so we have another model will be selected, right? So that's a problem that always happens with hypothesis testing, right, in this setting. And, well, whether we decide to add parameters from to a simple model or remove parameters from a complex model, the outcome could be different as well, right? So, again, whether it's this addition or removal of parameters, that depends on that, right? So that's a problem. So I came up with this kind of weird-looking picture was like kind of instead of, one of the problems was that I needed to decide some hypothesis, some order of the hypothesis testing, some order of parameters addition or removal, but maybe we can just, well, do some exploration like this where we start here or here and we like look at from here to this model, to this model, to this model, and we just take the path that gives us the highest p-value, right? So we make all the likelihood ratio tests or the smallest p-value, so we take that path, right? So we want to explore different options. Here, I'm not sure whether I'm going to add first like kappa or transition ratio or gamma, so that depends on which one is going to give me the best increase, right? So I move this space, but you can get trapped in local optima here as well, right? So I've done simulations and, well, this starts to get complicated. So after reading like a book by Burkham Anderson, I became like, you know, well, I guess I changed my mind. I realized that there were like other tools that were really simple, right? And well, I like simple things, right? Because I think that for biologists, which is where I care about, right? So I try to make things that they are appealing and simple for biologists that they can use to analyze the real data. The AIC was very convenient. It was a formal. It has like a sound statistical background, right? Comes from information theory. And, well, basically the AIC, the Akaike information criteria is an unbiased estimator of this information, the Kullback-Leibler information, which you might recognize as the entropy or things like that, which basically is, we're going to tell you what is the relative, the expected relative distance to the true model. So we have three distributions approximating a true distribution that is unknown. So the Kullback-Leibler information is going to tell us which model, right, is closer to truth. That's the idea. That's what it's trying to do, the AIC, right? It has this simplest, a very simple form, right? It's twice the likelihood plus twice the number of parameters. There is a reason why it's this, right? There's like proof of this. And basically, in the context of molecular evolution, is like the amount of information, right, we are losing just because we are using a model to approximate the real process of evolution. We can think of that. So we choose models. We want to pick up models that with the smallest AIC. There is like when sample size is smaller than the number of parameters, k, so there's a correction for a small sample size. That is the AIC corrected, AICC. There is also the baseline information criteria, which basically the BIC is twice the likelihood plus the number of parameters times the log of the sample size. And, well, with some uniform prior probabilities, it is supposed to be a good approximation to model probabilities, to the posteriors that, right, to the marginal likelihoods of the models, right? And it has this shape. That's supposed to be the case. So many times it's used as a surrogate for posterior probability. Instead of using some Markov chain Monte Carlo, we just use the BIC, which is to compute. Obviously, we need to have the maximum likelihood right first. That might take some time to get that. So, like a couple of years ago, there was like another criterion which basically is based on this is the BIC, but they wanted to incorporate some measure about phylogenetic performance, right? So they thought, well, what are we doing here? We're worrying about models, but most of the time we worry about models just because we want to estimate a tree, right? I mean, not always, right? I mean, just identifying the best fit model is a good way of describing the data, independently from phylogenetics, right? But most of the time the goal is to get a tree. So they thought, well, why don't we try to incorporate some measure of phylogenetic performance here? So basically they penalize the models. They penalize the BIC with a measure of branch lengths. So first of all, they use a fixed topology, although they did later a paper where that topology wasn't fixed. And with each model, they estimate branch lengths. And then they get the Euclidean distance, right, from every model to the branch lengths of the other model, which is this, right? This is the vector of branch lengths from model to model K, right? And they want that penalty is smaller if your branch length estimates are alike, right? Look like the branch estimates from other models, right? So if your branch estimates are really different from the other models, this penalty is going to increase. That's more or less the idea behind this, right? So with this penalty, right, you get a risk, right? This is in theory, and well, you get like a new criteria, right? That in simulations it was shown to work very well to get trees with accurate, not really accurate, somehow accurate branch lengths, which makes sense because it's based on that. Right? So that may be a good idea. Try to incorporate something about phylogenetics inside these statistical methods. And then there is, well, probably one of the most natural ways of doing this, which would be calculating, right, what is the marginal, right, likelihood, or what is the posterior for every model. And in theory, that could be done using reversible jump, MCMC. So just approximate all these quantities and just choose the model with the highest posterior. Right? But maybe that's not that easy to do in practice. Well, one good thing about this criteria, that's one of the reasons I prefer to use this than likelihood ratio test, is that we can have a feeling of uncertainty, right? So there are many models, many possible models, right? So we just want to work with one. Well, it might be good to have some measure of the uncertainty, whether our data supports clearly one given model or other models, or doesn't have a strong preference for any model, right? So that's very easy, simple to do because we can rank these values. We can rank the AIC, the ACC, the BIC, or the posterior, so we can have a rank of models, and we can see whether the second best model is far away from the first one or not, or is very close to, right? So that's the idea, right? And there are some rules of thumb for the AIC, might be this, whether this delta, this is the distance to the best model, right? So just pretty simple, just rank them. And with these differences, AIC difference, BIC difference, we can calculate something like weight, right? The weight of a model, which would be like, given this set of models, what is the weight, what is the credibility or the confidence I have in this model as being the best model for this criterion, right? So the AI, here I can put the AIC, the ICC, the BIC. The DT is not clear. I can put the DT here. We can calculate as that because the DT has the BIC inside. So what I'm using is a different weight that, by the way, doesn't work very well. And then posterior probabilities are actually the weights themselves, right? So that's a measure of evidence for a given model, right? Relative to the other models, right? So all of them add up to 1, right? So I can run the models and I can see whether I have a confidence or a weight in 99% in that model, or 20, and then the next one 18, 13. So that's going to give me a feeling about whether I'm getting, right, like good support for one model or for 5 models or for n models. Something like this. This is data we're going to see later. Basically, we can rank the models. Here, I'm ranking them with the AIC. This is the number of parameters. You see here like a large number because the branch lengths are parameters too in the model, right? So the distance to itself is 0, obviously, and this is the distance elect in AIC 2.1, 2.1, and so on. And then we calculate the weights, which is a way of rescaling this, basically. They add to 1, and the evidence for this model is 52%. Is that match? Well, I'm not sure, right? So once we have weights, we can build something like a confidence intervals or credible sets of models, right? So for example, a 95%, well, here we don't have any value that is 95%. The 95% interval will be here. But because we have a weight here, we can choose, this is GTR plus I plus G, has this 0.0344 weight. A little bit of it is inside the interval, right? It's inside the interval and other is outside, so we can throw a coin and in each case decide whether that model is going to be inside or outside the confidence interval, right? So that's a way of building an exact confidence interval. So we can do it. And then we might decide that instead of working with one model, right, if we really care about our tree, we might want to work with the 95 confidence interval of models, right? So it's more work, but we have more computer power now. Well, model averaging is a continuation of this, which is basically using these weights, right? These weights to get average estimates, right? It's also called multi-model inference because we're using a number of models to get single estimates of parameters. Basically, the idea is that, well, for every parameter that is contained, this parameter that is contained in a model, that's what this index is doing, whether it's in a model or not, we just make a weighted average of those estimates, right? So gamma, the shape of the gamma distribution is going to be in X number of models, imagine in 10 models, and any one of those 10 models is going to have a weight. So we're going to have 10 estimates and 10 weights. So we just make an average, right, of that, a weighted average of that. So we have now one estimate of the shape of the gamma distribution with 10 models, right? That's the idea. That the numerator, right, below this quantity here, right, which is the sum of the weights that contain the parameter of interest, is like a very straightforward measure of how important is that parameter, right? Is that parameter present in models that have a high weight or not? So that's going to tell you whether that parameter is important for us, right, to describe our data. And I think that that's a very simple way of describing your data. So you're going to see which parameters are most important for you. Of course, one of the parameters we might want to average over would be the topology itself, right? So basically, this could be like, well, the steps we might take. We can get likelihood for all candidate models. We can calculate the evidence, whether we use AIC or BIC or posteriors for every model. We get a tree for each one of those models, and we make a weighted consensus tree out of those trees. So something like this. Here we have one single data set and 24 topologies, well, 5 different topologies, right? 24 trees with 5 different topologies. The color means the same topology, right? With different models. Right? And, well, here, first of all, this shows that how models are important, right? Depends on the model I use, I get a different topology. Not always. With all these models, I always get the same topology, right? But the question is, should I just use which topology is the one I want to believe. The one with the highest likelihood, the one with that corresponds to the best fit model. That's what we've been using, right? In the past, like many years ago, we just choose one, right? Normally the one that was default in the program. So if you were using PAUP, this would be your topology, most likely, right? Because that were the default values. If you're using phylip, that would be your topology. Years later, when model selection came out, so you would choose just one of these topologies. So now, what I'm proposing, what I'm saying that might be a possibility would be like use all of them to get a single estimate, right? And here, these numbers are a measure of model uncertainty. Whether here 100% means that all models support this claim, right? All trees for all these models support this claim. They are not bootstraps or posteriors, it's something different. It's about model uncertainty. So in this way, we don't have to choose one model, right? Well, this is an example. I'm going to go quickly. Basically, with some real numbers, that's the sample we saw before. We can rank the models, right? Get a cumulative weight. We can try to build, as I said before, like a confidence interval. So we might want to work just with those models, right? That's an option too, because we have a reasonable amount of the evidence there. These are the estimates. These are model average estimates for the frequency of A, for example, and these are the estimates for the best fit AICC model. These are the estimates for the best fit H, the likelihood ratio test model, which is HKY plus I plus gamma. And you can see that there are not really many differences, right? So the estimates are normally pretty similar, right, for most values. And, well, here we didn't gain much, right? So actually, using the best fit model is as good as using the model average estimate. In this case, probably in most cases, I would say. Here, just one thing that you should notice that these are two different parameters, right? It's not the same, the shape of the distribution in a plus G model that in a model that plus I plus G, right? So we have the proportion of invariable sites there. That shape, that gamma distribution is a different gamma distribution, so don't get confused with that. We can measure the importance of the different parameters, right? So here, in all the important models, we always have unequal base frequency, but the transitional ratio is only in less than 20% of the models, right, that we care about. And, well, so for the different substitution rates, we have different, some are more important than others, and having a shape, a gamma distribution is very important, and a proportion of invariable is very important, right? So the relative parameter importance is a really straightforward and easy way of describing your data, which parameters are most important. This is the model average phylogeny, and this is the best fit AICC phylogeny, and there are a few differences there. Here, these are bootstraps. Here, these are multi-model support or model support, right? And there are a few changes here in the topology, right? But, well, in general, they agree quite well. This is the relationship between AIC topology. We have that models that have similar AICs tend to, not very strongly, right, tend to have similar topologies. So that could be an interesting relationship too, right? So similar AIC values, in this case AICs, tend to, so models that they are, right, the pairwise distance is kind of like very high between topologies. This is the Robinson and Fold distance, and this is the AIC distance. So models that have different AICs have different topologies. Models that have similar AICs have similar topologies, right? So that's a nice and expected relationship, but although it's not that strong. Although this is data dependent, obviously, right? This is just for that mitochondrial data set. Well, does this work? That's the question, right? And that's what I really care about, right? Because if it doesn't work, I won't bother more about this, right? So what I did is, well, or I'm trying, I mean, this was frozen for 1 year's work, but now I'm restarting this and I'm trying to find out, right? So these are really well-known empirical trees, right? These are maybe not as good as the topology that Michael Cusera showed us yesterday, right? But these are, well, biologists would agree that these relationships are true, right, in a sense. So we know, well, quite well, right, whether are these relationships or those in different families of insects and so on, right? Human, chimp, gorilla. So there are trees that are true, right, basically. So what happens when we do model averaging? Well, here the question is that these trees with some mitochondrial data, well, they are easy to estimate in general. So basically with the model averaging, we get the right topology, right, all the time, but we also get the right topology just using the best fit model. So we didn't gain much, right? And comparing whether it's worth it to do the model averaging versus just using the best fit model. And here it is not. But, well, this was just a check because I expected that. I mean, these are topologies, the signal is strong for those topologies. You know. So I did some simulations, preliminary one. So I chose one complex, the most complex model. So here, the true model is inside the candidate set of models, which that doesn't happen in nature, right? But I wanted to do this first. And this is like a difficult tree. And what I did is like simulate 200 data sets. For each one of them, build 56 trees corresponding to 56 models and get some estimates. First of all, well, I checked whether AIC identifies the true model. And, well, it does not. This is the generating model, that would be a better word, right? Which is that one. It gets stuck, if you want, in this model, which is just like that. But probably because these two values are very similar, right? So it collapses those values, and then we get this model. So that's not that bad, right? So actually, I did simulations in the past, and model selection tends to work quite well to identify the true model when that model is in the candidate set, right? How about parameter estimates with model averaging? So this is the estimate of the frequency of A, right? With the best fit AIC model. This is the model average with 56 models. That's the average estimate. And this is the estimate with the true model, with the generating model. And the red line is the true value. Well, we get the same, right? So there are slightly little variations. But again, there is not much gain estimating parameters. Just using the best fit models give us the right value, right? We don't need to go and estimate this from 56 models. How about the proportion of invariable sites? Well, it's also quite, here there is a little overestimation, but not much. But if we compare, right, the model average with the best fit with the true model, we get pretty much similar things. But this changes a little bit, and here this is probably the only result that I might want to explore further, which I'm doing right now, is about topology. So here we have the maximum likelihood estimate for the Robinson and fold distances, right? I know the generating tree, right? It was that small one, but difficult tree, right? So this is the true model. So the distribution of estimates of the, right, is centered around here, right? That's what this line is, that the true model, it's a difficult tree, right? We never get it right. There are really small, short branches, right? But we get this kind of estimate. So you can see that with different simple models, well, we do worse, and there is a lot of error, right? Then with complex model, we get also error. But here, it's very important to include the gamma parameter and the proportion of invariable sites, right? And if we have both a complex substitution pattern and a measure of rate variation, then we do, well, more or less quite well. This is a little biased, but it's a smaller error than with the true model. How about the model averaging? Well, if I use this is the majority rule tree, the weighted consensus. Well, I do, well, more or less quite well. I think that this was the mean or the median, I don't remember very well. But we do quite well. It's pretty much unbiased, and the error is smaller than that. But this is what somehow surprising, right? If we just do a strict consensus of all the trees for all the 56 models, that means I'm not going to use the weights, just do so I get a little bias, but I get a much reduced error, right, in my topological estimation. So that's curious, right? So I need to double check that, but it seems like that's actually true, right? That basically we reduce the variance. Actually, that's what is expected from model averaging. From model averaging, what we expect is to reduce the error, because we're using different models that capture different features of the data, and we're going to reduce somehow that error, right? But I was surprised that this performs better than that, because then all I just said is not very meaningful, right? But you just need to check it out. Well, parameter importance, we can measure and we can get different estimates of parameter importance, which here there is no a true value, right? I don't know the true importance of the parameter, but I get things that look, all the models contain this, right? Plus I plus gamma, right? Both parameters, I simulated with those parameters, so that's perfectly fine. The frequencies and, well, different parameters, they have different importances, but As I say, this is fine. This should be low because I didn't simulate right a transition restoration. I simulated a GTR, although there is. So what I did actually, I started to take a look at this last night. So there might be some mistake here. It's like more complex simulations, right? Where the true model is not one in the candidate set, and basically random trees, right? So I use the coalescent and to generate topologies and branch lengths, 20 taxa, almost 999 sites, and a mixed model with 3 GTRs, 3 different GTRs, like kind of simulating codon positions with parameters estimated from real data, right? From coding sequences from real data. So there are many ways of simulating complex models, right? And actually, that's a good question. How do we should simulate data in phylogenetics, right? Which kind of models should we use? Because there are infinite possibilities, right? And, well, and here, well, I evaluate 88 candidate models this time, right? So I'm increasing the number of models. And the 80 candidate models, so what I do is for each one of these data sets, I just estimate 88 likelihood trees and do this model averaging and do some measures. And what I got was, well, pretty much an agreement between all criteria, all the cases, right? Like the number of parameters is really similar, so this is not that big because we are going from 45 parameters to 47, so BIC and DT tend to select models with less parameters. The right number of parameters is 48 here. The weights, well, here I use a different scheme than for these 3 methods, so don't worry about this, the DT weights, because I just use the 1 over DT, 1 minus DT divided by the sum of that for all models as a weight, right? So that's a different kind of weight, but it doesn't work. And, well, that means that the confidence intervals for the IC are really narrow, and for the BIC tends to give like wider confidence intervals of models, right? So that's a trend that is there, right? Well, the best fit estimates are quite good and similar for all models, so there is not much to say here. And for the model average parameters, right, we get things that look nice, but it's the same for all models, right? So there is not much difference. So what I think it happened is that I just simulate under a really high substitution rate, or too high substitution rate, and the data has strong signals, and every method agrees pretty much in most things. These are the importance of parameters here. Well, here there are some differences. The BIC, right, considers, these are some examples, right, that to show you that in general they are similar. Don't care about the DT column because I think that weight is not useful. It's an idea, but it's not useful. And there are some differences, but in general they agree quite well. How about trees? How about the average tree? Well, here in this time we get the true tree many times, right? But the median is a distance of 2 from the Robinson fold distance. Like there's one clade swap. But they all, so this is the best fit model for these 4 different criteria. This is, even with Jukes and Cantor, we just get the same performance, right? So that's what I say, that probably this data is too divergent. It has 2 signals, and it's not worth it. So I need to tune up my simulations a little bit so to find something more difficult, right? But I just did this very quickly. Well, all this is implemented, as I said. I think that is important. Well, not everybody needs to do that, but somebody needs to do it, right? Somebody has to do this. That's right. If you propose a method, you don't need to write a software implementation. But probably if somebody wants to use that, probably somebody needs to write software, right? So we've been writing software for a couple of years, very simple one that actually I use other programs, right? I don't try to reinvent the wheel often, probably because I couldn't. But basically, here this is a model test that you might know that uses PAUP, that it's been there for ages, very simple tool. But actually, I think that the best thing about model test is that it encourages model selection. That's it, right? Which I think is important for phylogenetics, where you get all these. So all these things I talk about, you can get those with software tools. This is for proteins, which I didn't talk about. This is protest for proteins, so you can get that as well. This is implemented in a web server, also model test and protest, so you don't need to. That's pretty easy to do if you don't have computer power. And I'm finishing writing a new. Actually, it's like from scratch a new version of model test, this in Java, which doesn't need PAUP. Actually works with FIML. Does everything I just told you and compares 88 models, so I'll try to show you. These are the candidate models, right? The substitution patterns, all of these plus I plus G plus I plus G. Here I chose some schemes, right, that they seem they seem meaningful to me. And this is the pipeline. Basically gets several software tools, RedSec, FiMel, Consens, and actually gives you a model average phylogeny, right, with all the models, right? So it's not, I'm not averaging over the branch lengths, but that's something I plan to do. So, although, as I say, so far I'm not saying that this might be that useful. Well, how about some caveats and thoughts that, you know, we might have? Well, I think that the question is worthy, right? I've been talking for 40 minutes now, so is any worthy what I just said? Well, I'm maybe a little skeptical, right? Who knows? But it implies quite a bit of computation, obviously, right? It's not just anymore about getting just one likelihood tree that I remember 10 years ago, you know, we will have our computers with PUB for, you know, 7 days in the lab. Now it's much faster. We can do that. It is possible, but are you willing to do that 88 times? Would you normally, well, with clusters, things like that. So it's much more computation, okay? But on the other hand, I would say that, well, you don't rely on one single model. And different models, they can capture different features of the data. So if you have some way of, the right way of giving the weight for each model, right, combining that might be worthy, at least in theory. But simulations are not that clear about that, maybe. One important idea is that maybe in this context, it might not be that useful, but you can average over everything, right? So whether this model is better than that, or whether we should modelize this at the level of nucleotide or codons or proteins, or whether we should use model mixture with 3 models or with 5 or 7, model averaging can deal with everything. You can just average over whatever you want, right? So you can even estimate your tree with a codon model and then your tree with DNA using the DNA information, and then you can average over that, or so that's a possibility, right? Or if you're working with proteins, you can use an empirical model or a mechanical model, and then you can average over that. So the point is that you don't need to rely on a single model, right? So in my mind, I think that model averaging might be useful if you have time, you have a small, right, but difficult problem, right? So you don't have like a really large tree, like a small tree, but a tree that you really care about, that might be really important for something, right? I don't know, I'm thinking about the HIV dentist in Florida, things like that, like in trials, or just history of you know, apes or something with some ape. So some relations that you really care about, you have 8 taxa, 9, 20, or 50. This can be done with 50 taxa, actually. And you just really have time, and you don't want to put all your money, right, in one number in the casino. You want to play all the numbers, and that's possible with this, right? And I think that might be the case, right? Another idea, another thought is, what we are really fitting, right? So the history of life is a continuum, right? If we believe in evolution, there is something relating. So, well, even though that there might be some true model, right, with this, in this case, GTR plus I plus gamma, this might be like a subset of something that might be evolving, right? We're trying to fit one part of that. So the true model, imagine this case, that the true model here is GTR plus I plus gamma, right, in red here, but we are just working with this subset, right? Well, what are we doing here? What do we want? When we fit the model for this subset, right, of this whole thing, we are working with just this genus, for example, right? Do we want to approximate the best fit model from a statistical point of view, or we just want to approximate the truth somehow, this model, right? That's a question that, well, might be discussable, what we are doing, right? And that's related to another question, whether that many people ask me sometimes, whether, well, when we're fitting models, should we use the outgroup? And I would say yes, right? Because I'm more of this kind of, I'm thinking about this, right? So I'm more oriented to think that I'm just trying to do is just fit the data I see to a model, right? I'm not saying anything else about that. So if my data includes an outgroup, because in my tree I'm going to have an outgroup to root the tree, just include it in the model selection procedure. But that might be some things that might be bad about that too also. Well, some technical questions or even mathematical questions, right? So Akaike said that the Akaike weights are an approximation of model probabilities or model likelihoods under some forms of the prior, right? And well, how are they good? Are they any good, right? Especially we know that models are misspecified. Models of molecular evolution are always misspecified, right? They are not true. None of them. They will never be true, right? So they will be always misspecified, right? So many theory, right, they rely on having the true model, right? But that not happens here. Never, right? So how do we KK weights approximate like posterior probabilities, for example? Or can we compute this efficiently, right, with rejection Markov chain Monte Carlo? I think it would be very difficult, right, it seems like to calculate this for 88 models, especially if you need to work with weight factors 2 by 2. So is this possible today to compute, really do this under a Bayesian setting? Another application which I think is going to be pretty nice or pretty important is that phylogenetic data, right? So multiple genes, right? So one option might be like if you just have 5 genes or 5 partitions, right? So you can just fit every partition independently, and that will be the same thing as minimizing the AIC, for example, right? For each partition. That's a very simple and naive strategy. Other is try to find combinations, right? And I wasn't here, but I listened to your talk, Barbara, which was pretty nice, actually. It's pretty nice to listen to the MP3. And that's a really nice way of selecting models for partitions, right? We can use also genetic algorithms, right, to search among the possible combinations of models and partitions. Obviously, a good idea is to reduce that number of partitions, right? And if we don't want to reduce, in your talk, you have like a graph with different AIC for different number of partitions, right? So you can mobilize your data with 1 partition as a whole, 2 partitions, 3. So you can average over all those estimates as well with this. So you don't need to rely on one, right? So it's a different point of view. It's just, as I said, not putting all your money in one number. So. But it takes more time, right? So it might not be worth it. That's the thing. Right? Another thought might be, well, how do we choose candidate sets? Because, I say, well, I put 88 models in. But, well, I think that it should be a priority. I think so, but, well, somebody might say, well, you might try to learn from the data something, but that might be circulars and so on. So I don't know. That might be something interesting to talk about. How do we define the candidate sets models for our data, right? Should we do that from a biological point of view, just applying our knowledge, or whether it's a mitochondrial gene, or it might make sense to that? Should we abandon very simple models, right? Should we include Jukes and Cantor in these sets, right? If we are working with, I don't know, the tree of life, right? So I don't know what you think. So there are some decisions and some things, right? And, well, everybody is proposing a challenge, so I'm going to propose my own challenge here, which is this, right? So I talk about sample size. To calculate the BIC and the AICC, we need to know what is the sample size of an alignment. So what is the sample size of an alignment, right? It is the number of taxa? Probably not. The number of sites? For me, that's something closer, probably. But it's the number of variable sites, or the entropy, or some measure of information or variation, diversity in the data. It is the number of sites or number of taxa, because, well, we can have the same number of sites but different number of taxa, right? I would say that actually we need to care about what we're trying to estimate, the phylogeny, and if the number of taxa is different, we're talking about a different parameter of interest. The phylogeny is a different phylogeny. So I don't think we can compare the sample size of data sets with different number of taxa. We just need to worry about, I think it's not comparable, right? But I don't really know what is the sample size of an alignment. And what I use normally is just the number of sites by default. But that doesn't have to be right. So this might be proof, probably mathematically, I don't know, what would be the sample size or statistically using some techniques. I don't know. I've been doing some simulations but from an empirical point of view, right? So what would be the sample size that give us the best topology, right? So that's one way of doing it. But I don't have any clear results. But what I tend to use is this or this, right? But that might be an interesting theoretical question for you guys. And, well, last night I'll try to attempt to answer or how do we say, well, the challenge proposed by Michael Cusera, and, well, it seems like I didn't get it right? So basically I got a couple of sequences, I aligned them, and, well, and I use model averaging, right? So I estimate 88 trees, and this is the average. The support is 1 for all of them. You can get it in the picture, right? But I don't know what you think. It's not similar to the tree that you put in your PowerPoint. I have to say that I only use 300 sites. I use I filter the alignment because there are regions, but well, I'll try it again with the right alignment. He's gonna try to give me. It was pretty dirty, right? But well, at least I tried. And if I have a second, So very quickly, so I'm going to show you, and this is going to be available pretty soon. Where is this? Like here. So this is the new program. So I'm finishing, I hope, that no, that wasn't right. So that is going to let you actually do and explore. Well, okay, so you can get a simple data set here. You're going to have the option. Oh, actually, it's in front of me, sorry. It's quite deep. Right, so here you're going to be able of choosing what is your candidate of models, whether you want to include models with different number of substitution schemes or parameters, whether you're going to estimate your tree. That's something I didn't talk about, whether you use a fixed topology to get all these likelihoods or you optimize also the topology. That turns out that it doesn't matter, really. You get the same results pretty much, but if you use this, which will be the optimal here, this is a really small data set, so what the program is doing now is sending commands out to PhyML, and PhyML is doing the hard work, right, which is getting all the parameter estimates, but this is quite fast. This is like a 6 taxa, 500 or 600 sites, but it's going to take half a minute to get the 88 models. I would say that this is doable with 50 taxa or thousands of sites. If you want to wait, you can wait a couple of days, right, don't you? And well, we're going to the likelihood, the parameter estimates, and you're going to be able of, well, getting the AIC. This is again here, right? So you can do, well, confidence intervals, define your own. You can do the AIC calculations are here, all the parameters. And then, if you want, you can get like model average phylogeny with this criteria or the others. You need to calculate those first, right, to get the tree weights. You will get something like that, and you cannot see it for some reason. But well, here is the topology with 88 models, right? So that's doable, right? At the end of this year, this is going to be available, so you're going to be able to explore this further. But I don't know how useful it's going to be. I don't know your thoughts. And well, good that it's time to stop now. Okay. Thank you.
There's time for a question or two.
David, I'm just trying to understand your model averaging phylogeny in more detail. Your first step is to work out the model average parameters for a series of models. Is that correct?
Right, and you get the maximum likelihood score, right?
And then do you take those model averaged parameters and now subsequently reapply them in the...
No, it has nothing, well, that could be, that's a possibility, yeah, actually, that I never thought of. Actually, it's independent. You get average estimates for different parameters, right, and the tree is another parameter, right?
Okay, so then when you average your trees, right, you're not weighting the average trees by the likelihood scores or by the AIC?
Yes, I do.
You do?
Yes,
okay,
by the AIC weights. It's a weighted consensus.
Right.
But in the simulations, what I saw is that if you actually don't weight them, you give a weight of 1 over the number of models, the same weight, a strict consensus there. Basically, you just get a smaller error, which is surprising. I'm not sure why. So, but that's the idea. But you could do that. You can get model average estimates, and with those, estimate again a tree. That's interesting to explore. I think that Barbara.
Yeah, just a sort of a general comment, I guess. So people think a lot about sort of relative tests of model fit and things like that. Is this model better than another one? But I guess not so much about, is this model any good at all? Like, I mean, to what extent do you think
right,
we sometimes ask which of these hats looks most like this elephant?
Right. No, that's a question. Right. That's the second view on model selection is whether is the general fit, right? Whether and the usual test is comparing the fit of a model against the multinomial distribution, which is the best explanation you can get of your alignment without thinking of trees or anything. And well, most of the data sets fail that test. It's too stringent. So I think it was Box who said that all models are wrong, but some of them are useful. So we hope that some of them are useful. So I think we are far, what is my feeling? We are far away from truth in the sense that we don't have all the parameters, but I think we have a good representation of the most important features, because what other things might be there? Well, obviously there are base frequencies, can be different or not. There is great variation. I mean, obviously there is structural issues if this is like a coding gene or is in a ribosomal gene and so on. I think we do quite well. I think that models are reasonable representations. That doesn't mean that we don't need to go further, and I think that, well, yeah, we should go for more complex models. But then we don't need to rely only on those complex models, because sometimes we won't need to. So that's the point of model averaging. The question is, so far it doesn't seem to be that useful, but it might be in the future for other kind of things. I don't know, for what you are doing, like you try to choose what is the best number of partitions, right, of classes, of gene classes and so on. Well, maybe you might find that you have, class 4 and 5, they have similar AICs. Well, so which one do you choose? Both. So that would be maybe the most of the case. But I think our models are useful descriptions right now, but they can be improved.
Okay. Actually, I think we better hold off and give a little time for the transfer, so maybe you could ask your question later.
Oh, of course.
Thank you very much.
Thank you.